variation or fast variation. Okay, so we'll explain this in more details. We will have a mathematical formulation as well, and also at the end of today's lecture we will speak about the third assignment. Okay, so like keep in mind we have fading. This is what we are suffering from when we send the signal over a wireless communication channel. You have a fading. This fading can be large scale or a small scale. In a small scale, there is two different point of views. Okay, so we can have actually time. We can look at the time spreading from the perspective of time spreading. In this case, we can have a coherence bandwidth, or like we will define everything later on. And this type has two subcategories: flat, or frequency flat, or frequency selective. Or if we look at the coherence time, we can have what is called a slow variation or fast variation. Okay? Before we go with all these details, what this means, what that means, we need actually to discuss some concepts. Okay? So as we can see here, we have like coherence bandwidth. What is coherence bandwidth? We have coherence time. What is coherence time? Okay? So we will speak about these terminologies, and then we go ahead with these categories. So again, this is from like 2 lectures ago. We have the time spread. So the time spread is the difference in arrival time between the earliest one here and the latest significant, right? So the latest significance is not the latest one, because the latest one might be very weak, okay? But the latest significant one, okay? So due to the multipass, we discussed this in more details 2 lectures ago, or 3 lectures ago. Okay, so as we can see here from this one, this is the replicas here. This is the first version or the first copy of the signal. Due to maybe a line of sight or maybe non-line of sight, it's okay. But this is the first or earliest one. And I have another replica, third replica, and so on. And maybe we can consider this one the latest significant replica or copy of the signal. In this case, the time here might be referred as tau or time spread. Okay, so this time, typically without any kind of multipath, I have tau equals 0, right? Without any multipath, I have only one received signal. But unfortunately, because of this multipath effect, I can have multiple versions similar to the echo of your voice, right? Like in wide area. Okay, so the difference between the first one and last significant one is called tau, okay, or the time spread, and we actually we saw some numerical values about what is the practical range of it, and again it depends on the nature of environment, indoor, outdoor, even indoor, if it's like a shopping center or just office, how many people there, what's the structure of building, it depends on many factors. Okay? But anyhow, we have this, the definition of time spread is the time difference between the first and last significant trend. Okay, so this is time spread, and keep this in your mind, and this is due to multiple. Okay, and we have what is called a coherence time. Okay, so for coherence time, this is a statistical measure of time duration over which the channel impulse response is essentially invariant. Invariant means like the variation over time is very limited. Okay, so typically I have like time invariant channels. Time invariant means that every time, like for example, if you look at this channel now, this channel maybe after 1 hour after we leave this place, the channel will be changed, right? So like if we make some communication here in this room, we will have a certain channel properties or statistical behavior. Statistical means that the randomness, right? Because again, the channel is random. Random, why? Why it's random? Because first of all, I don't know how many objects. the objects might be moving, the transmitter might be moving, the environment itself might be changing over time. So I have random environment, even the interference, even if we have a fixed environment, a fixed objects, a fixed like people here, but you don't know how many signal will interfere your signal. So everything is random, okay? So the statistical behavior mean that when you study this randomness, for sure there is some kind of a statistical behavior of it, okay? So this is statistical behavior when it change over time, right? So like again, return back to our example here in this room, like the environment or the statistical behavior, if we have like 50 students or 50 people here, for sure the communication will be different if this is empty place. The communication will be different if this one is completely empty, without any desk, without any computer, without anything here. Completely different if this ceiling, the height of this ceiling will be different. So the statistical behavior of the channel will change over time, because you don't have actually a fixed environment. And maybe in some rare cases you might have fixed environment. So typically we have a variable environment changing over time. But again, we need to send the symbol, okay? And I don't send the symbol forever. I have a limited duration for the symbol, okay? So we divide this time invariant, or the variation over time, we divided it in a small periods, which we can consider this period, the statistical behavior almost constant over this duration, okay? For example, a simple example about that, the ears, right? So the ears, there is a big debate like in the last few days, last months, about is it like spherical or whatever, but like consider it, the curvature of ears here is a spherical one like that, okay? So even this curvature is a spherical, but if I take a small piece here, I can consider it a straight line, right? Okay, so even you have a variation over time or whatever, I can take a small period, and this small period of time, I can consider the statistical behavior, not the variation. I'm speaking about the statistical behavior. The statistical behavior means that the distribution, the randomness, the variance, the mean, right? So this means the statistical behavior. So I can take this and call it TC, or the coherence time. So the definition of coherence time is the statistical behavior over this time duration, like when we consider the channel remain approximately constant, okay? So like if you extend over this TC, or coherence time, in this case you might experience a different distribution, a different randomness, a different statistical behavior, okay? So is it clear? So for coherence time, like for example, according to the channel itself, the coherence time will be variable, okay? So I might have, for this channel, the coherence time is this amount, maybe for another whatever, another channel, maybe this is the coherence time now, okay? So the coherence time is the statistic, or the period of duration, or duration period, that we can consider the statistical behavior of this channel will be like fixed or approximately constant. And actually this kind of coherence time is related to the Doppler effect, okay? The Doppler effect is related to the movement, okay? So for sure, if I have everything is constant, then the coherence time is a certain value. But if I start to notice some movement, in this case, the channel response, this is the channel response, right? The channel response, or the channel characteristic, will be changing with the movement of the objects, or the transmitter, the receiver, right? So there is a relation between the coherence time and the Doppler, right? So like if I have, it's like inversely proportional. I made it like approximately because this is not the exact rule, okay? So the exact rule, it depends on the environment. Actually, there is a factor here, and you can see when you, when we speak about the third assignment, you will be given two names of two papers, like popular papers, and you will see the exact rule that is used in practice, okay? But for problem solving or the numerical results we will be solving, we will consider that a TC is inversely proportional with the Doppler frequency, okay? But that's why I used like approximately equals, okay? But it's not the exact one. Okay, so again, the exact one you will see it in the paper. But during solving any problem, we will use this formulas, and there is some kind of approximate formulas here because I need just to pick up the concept only, right? So like I need to pick up if you try to increase if the movement of the environment or the transmitter or receiver like moving very fast, in this case the Doppler frequency will be increasing, right? In this case, the variation of the channel will be like varying a lot. In this case, TC will be reduced. You cannot take wider TC. Okay, does it make sense? So again, before we leave here, TC, the coherence duration is the period of time that I can consider the statistical behavior. It's not any behavior. Statistical behavior is almost constant, okay? And it's inversely proportional with the Doppler frequency because it depends on actually the movement of the object, okay? Okay, so let's see here this numerical example. Okay, suppose that I have like moving a mobile user with a velocity of 60 kilometer per hour. Remember, I need to change or convert this from hour to meter per second. And I am working at operating frequency of 2 gigahertz. Okay, so I need to calculate the coherence time now. So to calculate the coherence time, I need to calculate the Doppler frequency, okay, and the Doppler frequency is, we calculated this last lecture, and then I will obtain this 111 or 111 hertz. In this case, the coherence time will be almost 9 milliseconds, okay? So for these kind of channels, for like every 9 milliseconds, I can consider the channel, the statistical behavior of it almost constant, okay? After this 9, I have another coherent time, okay? If you understood the coherence time, then we like the same concept with, but in frequency domain, we have what is called the coherent bandwidth, okay? So we compare the coherence time to the impulse response, but here we this is the same concept but in frequency domain. So like a statistical measure of the frequency range. Now we will not measure the period or the duration. Now we will look at the frequency range, okay? So the frequency range over which wireless channel frequency response is approximately flat. Okay, again, if you have random channel, random everything, for sure the frequency response of that channel will be random as well. Okay, so I will take a small period or a small range of frequencies, and if this small range of frequencies can be considered as a flat, in this case I can name this period or this frequency range as a coherence bandwidth, okay? And the coherence bandwidth is also like inversely proportional with that time spread, the delay time spread I just explained here. This one, okay? So again, this is not the exact one. The exact one, like some books, like if you, why I didn't put the exact one, because the exact value depends on, that's why I give you the third assignment, okay? So the exact one depends on the environment itself. So in some cases, this equals 1/5 delta T over T. In some cases, 1/50 term, right? So it varies based on the nature of the environment itself. So for the general purpose, it just BC, or the coherence bandwidth, is proportionally or inversely proportional with the inverse, or proportionally with the inverse of the coherence delay spread, or root mean square delay spread. Okay, so now after we understood what is coherence time, what is coherence bandwidth, and also what is the delay spread, we need to return back to our map here. So we will be discussing these two major categories of small scale fading. Okay, so we will discuss in more details what is would be here. We have like coherence bandwidth. What is flat frequency flat fading, and what is frequency selective one? Which one is better than the other one? Okay, and here after that we will be discussing what is slow variation, what is fast variation. Okay, so now we will be discussing these 4 types, but I need you to remember that frequency flat, frequency selective belongs to time spreading, and slow variation, fast variation regarding to the time variation perspective for a small scale fading. Okay, so let's go to a frequency flat fading. Okay, so frequency flat fading occurs when all frequency components of the signal experience the same fading. Remember, like most of these types you need to memorize, but all these types are super logic, right? So just try to understand them. Okay, so frequency flat. Frequency flat. So I'm looking at the frequency domain, right? Frequency flat. Okay, so remember I have 2 definitions. I have coherence bandwidth and I have coherence time. I said that the coherence time or the coherence bandwidth is the range of frequency that the frequency behavior can be considered as a flat, right? And here this type is called the frequency flat fading. Okay, so in this case, when you compare the bandwidth of the channel, it's supposed to be experienced to a flat fading, which means that the bandwidth of the channel, BS is the bandwidth of the channel, smaller than the coherent bandwidth. Because, like, for example, if I consider this is the coherence bandwidth, BC, okay? And we define BC as the range of frequencies that the frequency response can be considered as a flat. So in this case, if I have BS, which is the signal bandwidth, for sure it might be something here, right? So inside or smaller than the BC, okay? So in this case, the condition to have a frequency flat fading is the signal bandwidth smaller than the coherent bandwidth. Because if this signal is greater than the coherent bandwidth, in this case, part of the bandwidth will experience a flat frequency, but the rest of the signal will experience another frequency variation, right? Okay, So the condition here, and again here, this is the definition. It came from the type itself or the category itself, frequency flat fading, when all frequency components of the signal, here this is a frequency component, this is the signal. Okay, when all the frequency components of the signal experience the same fading. Okay, and this typically when the signal bandwidth is less than, this is the signal bandwidth, is less than the channel coherence bandwidth. Okay, or like you can actually, this is the main definition, but also you can replace BS because I have a direct relation between BS and TS, right? So like because BS equals 1 over TS, the time, the symbol duration, right? And here also I have a direct relation between BC, all right, coherent bandwidth, and delay spread or root mean square delay spread. So I have also 1 over tau here. This is a BC. So in this case, you can write the condition as BC smaller than, BS bandwidth of the signal smaller than BC, or you can write it as here TS greater than tau, right? Which makes sense, okay? So do you think that for sure any fading is something I don't want, right? But here, if I experience to a flat frequency response, in this case, it's easy to deal at the receiver side, okay? Which means that this is something I can deal with at the receiver side, which is something good, right? Okay, for sure fading is bad, but I can deal with it, right? I can correct the error, I can multiply by the inverse of frequency. I can make what is called equalization. We will talk about equalization by the end of this semester, maybe in the last week of this semester. We will talk about equalizers, wireless communication equalizers. So here, this is from the perspective of this is something I can deal with, this is something good, okay? So BS smaller than BC, which means that the signal will experience to the same condition, right? So something very fair. Similar to, for example, you are 50 students or 40 students, whatever. So you would like to be treated similar, like everybody treated with a similar treatment, right? So to be fair. So the same thing, if for the signal, I need the signal to, the frequency component of the signal to be treated equally. In this case, if you have the signal bandwidth smaller than the coherence bandwidth, so you can guarantee that your signal component will experience the same attenuation, the same everything. But if some of you treated unsimilar to the others, this is unfair, right? So like, if this signal bandwidth is greater than the coherence bandwidth, in this case, part of the signal component will be treated like, will be experience certain attenuation, and the others will experience another attenuation, and then we can have what is called a distortion, okay? Anyhow, so this is the main definition, BS smaller than BC, and like if you convert it to TS greater than tau, this is also like good from the perspective of time. This means that the symbol duration is greater than the time spread. Remember what we said at the beginning of this module. This is the time spread, right? When you experience this tau, I told you need to send the symbol after this tau, right? So if your duration of the symbol is greater than this tau, this means that you will not have inter-symbol interference, or you have a minimum interference, okay? But if your symbol is smaller than this duration, this means that you send another symbol before the first symbol ends, okay? So this is actually makes sense with this one here. So I have the symbol duration is greater than the time spread. Okay? So, and this is a key characteristic of it. A channel is a flat over signal bandwidths. No frequency components are distorted related to others. The symbol interference, there is symbol interference, intersymbol interference, but it's not significant. Okay, and typically occurs in narrowband signal. If you have, because the signal can be divided, any original signal can be divided to narrowband signal and wideband signal. Okay, according to the nature of wireless communication system you are designing. So for narrowband signal, I know that the bandwidth, the original bandwidth is small. So this will increase the chance that the bandwidth of the signal will be smaller than the coherent bandwidth, and then in this case you will have a fading, but this fading is easy type of fading, which is a flat fading. Okay, so typically with narrowband signal, which means that the bandwidth itself is relatively small. What about frequency selective? This is totally opposite of what we just discussed, a frequency flat. So frequency flat, now I have frequency selective. Frequency selective means that I select some frequencies out of the bandwidths, because the signal bandwidth, see here, this is the signal bandwidth. This is the signal bandwidth. Okay? So suppose that I have channel, this is the signal, I have a channel like that. Let's say change the color. How can we change the color? Green. Okay? So suppose that I have a frequency response of a channel like that. Okay, this is a channel. In this case, because not the whole signal experience or the whole signal components, the frequency component of the signal, do not experience the same behavior from the channel, this example, I will select these components from the signal to be passed without any significant distortion, but maybe this one will dropped, because when you multiply the frequency response of the channel times the bandwidth or the frequency response of the signal bandwidth itself, in this case this kind of a small variation or a small drop will select or will vanish some component of the channel. In this case, that's why this is called a frequency selective. Okay, so I select some parts of the signal components to be transmitted. So typically this happens when we have the signal bandwidth itself is greater than the coherence time. Okay, this is typically opposite of the previous one. So now I have a bandwidth here of the signal greater than the coherence time. In this case, for the whole bandwidth, it will experience different coherence bandwidths. Okay, so I will have what is called a significant interference. Some frequency components will be distorted relative to the others. Okay, and this signal experience a distortion, right? Because I do believe that in the past, the first course in digital communication, you studied what is the difference between distortion and distortionless. Okay, so distortionless means that all the signal experience the same, the amplitude, the whole components of the signal experience the same attenuation. Okay, and also the phase will be changing linearly. But if you have some components experience, again, for example, if your marks in a certain exams are low, and I need to multiply by a certain factor, all of you, I multiply by 2 or 3 or whatever. So I didn't make any distortion in the whole class because the low mark will still have the lowest mark, the highest mark will still have the highest mark, but I just multiply by a certain factor. But if I took some students and I multiply by 5, and another students multiply by 10, another students multiply by 0.5, right? So in this case, the arrangement will be changing. In this case, you experience what is called a distortion, okay? So if I have the whole signal components experience attenuation, but this attenuation with the same factor, in this case, I don't have any distortion, right? Because I can tackle this at the receiver side by multiplying by the opposite value, okay? So if the signal attenuation was 0.1, for example, I will multiply at the receiver side by 1 over 0.1. So I will return back the whole original value, okay? So here, for frequency selective fading channel, I experienced some kind of, the signal bandwidth is greater than the coherent bandwidth, and I have what is called a distortion because of multipass with different delays. Okay, and typically occurs in wideband signal. If I have wideband signal, in this case, I most likely because typically this coherent bandwidth is in wireless communication is relatively small. So if you have a high bandwidth or wideband system, in this case, you most likely you will be greater than the coherent bandwidth, and you will experience what is called a frequency selective channel, which is commonly used actually in our communication. This is something unwanted and very difficult to treat, right? But successfully we treated it because most of modern communication like OFDM, like signal frequency division multiplexing, is suffering from this kind of frequency selective. Okay, so this is the two types. This is the two types here of small scale fading when we look at time spread, right? Frequency flat, frequency selective. And again, for frequency selective one, you can convert this one to tau and S, right? So you can write it here. This is TS, and this is tau, and this is like, in this case, you have the delay spread greater than the duration of the symbol, and in this case, you have a significant intersymbol interference. Okay, so let's study this example. You are transmitting a signal in our list channel that has a root mean square delay spread tau of 0.3 microseconds. We need to compare the fading conditions for the two signals, the following two signals. I have a signal A with a bandwidth of 100 kilohertz and another bandwidth with 5 megahertz. Okay, the bandwidth of it. Okay, so first of all, I need to calculate the coherent bandwidth. The coherent bandwidth is, again, we consider it 1 over this value. In this case, we will have 3.3 megahertz. This is the coherent bandwidth. So since I have two signals with two different values of bandwidth, so if you compare the first signal of 100 kilohertz, which means that 1.1 megahertz, compared to BC, in this case, which one is greater than the other? So like BC here, the bandwidth, the coherent bandwidth is greater than the signal bandwidth, okay? So, and in this case, the whole signal, the entire signal, can see similar channel gain. And in this case, I have what is called a flat fading, because the frequency can be considered flat over the signal bandwidth. But look at signal B. If you have 5 megahertz, now you compare it with a coherent bandwidth, and you find that the signal bandwidth is greater than the coherent bandwidth, and in this case, some different frequency components of the signal will experience different fading. So in this case, I have what is called a frequency selective fading. Okay, so and again, if you remember, we said that with low value or narrow band signal, most likely we have a flat fading. For wide band signal, we have frequency selective fading. But again, don't rely on these values because you don't know, because you just compare value by value, right? So we don't know if this value is great or is large or small. We compare it, we must compare it to coherent bandwidths first before we judge. But like typically, I expect that the lower frequency or narrow band signals that most likely will experience a flat fading, but for a wide band signal we experience frequency selective fading. Okay, so this is the first two types regarding to the coherence bandwidth. What about the if we look at the coherence time? Now we will look at the coherence time. We have a time. Again, we have the fading. We define the fading as a variation of the signal. If this variation of the signal is slow, there is a variation. We agree about that, right? But if this variation is slow, we can call it slow fading. If this variation is fast, we can call it fast fading or fast variation fading. Okay, so what's the condition for it? Like this is the definition: the channel remains approximately constant over symbol duration. Okay, this means that because you have multiple symbols, I sent a symbol, another symbol, a third symbol, and all these symbols experience to the same behavior. Okay, in this case, I can say that this kind of a channel is a slow varying channel. Okay, like for example, if you visited St. John's today, right, and you look at the stores, everything, and you visited it after 10 years, it looks the same. Another 10 years more, it looks the same. So you will think that the variation of St. John's is slow, right? Because it's almost the same over duration of time or symbol duration or duration of periods. Okay? But if you every second, like you sleep and you woke up and you found something is different. When I was in Belgium like 10 years ago, it was like that. It was fast variation actually. Okay, so like when I go back to my home country for a vacation 1 week or 2 weeks, I found a new building, a new thing, so actually it was fast variation. Okay, so here, slow fading, the channel remains approximately constant over several symbol duration. In this case, the coherence time, because remember I look at the coherence time, so the coherence time greater than, like much greater than the symbol duration, okay? So you have multiple symbols can be transmitted over the same coherent time. Remember what is the definition of coherent time? The statistical behavior or the period of time that the statistical behavior is almost constant or almost the same, okay? So during this coherence time, you can send multiple symbols, okay? So what's the translation of it? TC, or the coherence time, is greater than, much greater than the symbol time. Or you can also, like, because I have a rule, like a relation between TC and FD, I have a relation between TS, the duration, and the bandwidth. You can look at here. You can convert to this one. But this is the main concept. This is the definition came from here. Okay, but this is the alternative one using the formulas. So this typically happens when we have a slow movement. Okay, this is nature. If you have a slow movement or almost a static channel, in this case, you experience that a slow variation in this channel. So appears like gradual variation in the received signal and mostly affect the amplitude, not the frequency or phase, right? Because of the slow variation. The fast fading is totally opposite, right? So if I have significant variation even during the same symbol, so I couldn't actually transmit the symbol before I finish the symbol, I notice a variation of the channel, okay? So in this case, this is very fast or fast fading. So the condition for that is the coherence or the symbol duration is greater than the coherence time. The coherence time is the period of time that the channel, the statistical behavior of the channel is almost the same. So like suppose that this is the time duration, right? This is a TS, this is a time duration, and unfortunately within this symbol I have only one symbol with duration of TS, but unfortunately I have multiple TC here. I have another TC here, whatever. So each symbol here will suffer from different coherence time. Okay, so this is a translation for it. The coherence time, unfortunately, smaller than TC, or you can convert it to the Doppler effect. The Doppler effect is greater than the bandwidth of the channel. Okay, so the Doppler is great or larger than the bandwidth. Okay, so this typically happens when we have a high mobility, unfortunately, which is true in some of the communication, like fast moving vehicles, or sometimes in flights or whatever. Okay, so if you are driving very fast, you will experience not only, we studied actually the effect of Doppler, right? When you increase the speed, you will increase the Doppler effect, and in this case you will have mismatch between the operating frequency and the frequency you will receive. And also you will suffer from fast fading channels. Okay, and the effect of it, rapid fluctuation of amplitude and phase, and can cause loss of the signal coherence and increase, of course, the bit error rate or the errors. Okay, so let's finish this lecture with the following two examples. Okay, so I have a wireless communication system operates at a carrier frequency of 2.4 gigahertz. And I have a mobile user is moving with 15 meter per second, a speed of 15 meter per second. Okay, so it's just like very slow moving, right? So like someone is walking and talk to someone like using a mobile phone. This is very small moving. Okay, so and the system uses a symbol error, a symbol rate. So I have RS with 10K symbol per second. So I need to identify the type of fading here. Is it slow or fast? So from this rate, I can obtain TS. Okay, so by inverting this, so I have this rate RS 10K. So in this case, I have time duration is 0.1 millisecond. And from this speed, I can calculate the Doppler, okay? And from Doppler, I can calculate the coherence time. And at the end, I will compare the coherence time with the symbol time. Okay, so as you can see here, the coherence time is 8 milliseconds. However, the symbol duration is 0.1 milliseconds. So I have a large coherence time compared to the symbol duration. So fortunately, you can send multiple symbols over this coherence time, which is something good because you have a slow fading. However, if you increase the speed to be 250 instead of 15, right? So you increase the speed, right? So now you are, instead of walking, you are like taking a train or aircraft. I don't think aircraft will will like move with this speed, but maybe. Okay, so and the symbol rate dropped from 10K to 1K only. Okay, so now I need to identify also the type of fading. So I calculate the Doppler frequency here. I will find the Doppler frequency now because I increase the speed. And instead of having 120 hertz, now I have almost 2K, 2000, right? So the Doppler increased. And from Doppler, I can calculate the TC, right? And also I can calculate TS from the symbol rate, and then I obtain 1 millisecond, okay? So I will compare two quantities together, and then I will realize that unfortunately the coherence bandwidth is smaller than the time duration, and in this case I will have what is called a fast fading, okay? So like just to remind you, this kind of easy rules, it will not be included in formula sheet, okay? So like if I decided to bring such as these problems, but again, you experience or you expect that like big formulas, it will be included in the formula sheet, but I cannot include in the formula sheet TC equals 1 over FD or TS 1 over RS, right? So like the easy formulas, and also I will post the formula sheet of the final exam 1 week before the final exam, okay? So you will be familiar with what the formulas you will have, and the rest you should memorize. Okay, so to summarize this one here, maybe I forgot to add a map. We can add it here. We can add it here actually. I can have, this is tau, right, or tau max, right, and this is, let me see, this is what? This is TC, right? TC. Okay, so for example, if I have a time or a symbol duration smaller than TC, okay? So what is inside here? Like this is 4 squares. Okay, so what will be here is slow fading, right? Okay, and if the symbol duration is greater than this TC, I will have a fast fading. Is it correct? Okay. This is regarding symbol duration. Here as well, this is symbol duration or TS. Okay. And if we look at back here, if we have the symbol duration smaller than tau, in this case I have frequency selective, right? Here, the symbol duration is smaller than this tau and greater than tau, right? Oh, this is this one here. Greater than tau, okay, we will have a flat fading. Okay, so return back here. If we have this is supposed to be TS. Okay, guys? Then this is supposed to be TS. Okay, so if we have tau greater than this one, the tau here, or this is TS as well, if we have a TS greater than a tau, in this case I have flat fading, right? And if I have in this area like tau s or TS smaller than tau, in this case I have a slow or frequency. Oh, this one is smaller than them, so this is frequency selective. Frequency selective, and here this frequency flat. Okay, so I will plot it in a nice way, and I posted it with the updated one. But what I need to discuss here is you might experience two types, right? Two types at the same time. You can't experience three types or four types. Why? Because you can have slow or fast. You cannot have slow and fast at the same time. You can have frequency selective or frequency flat. One of these types only. Okay? But you can have frequency selective with a slow fading, or frequency selective with fast fading. You can have frequency flat with slow fading. You can have frequency flat with fast fading. Okay? So, and what is the best option I can have out of these? Because I have like four possibilities, right? Flat, slow, flat, and slow, right? I might have flat and fast. I might have selective and slow. I might have selective and fast, right? What is the best option you can achieve actually, or like the best channel you can have actually, or you can deal with? Flat and slow. This is the best one, right? And the worst one is selective and fast, right? So selective and fast is the worst channel you can deal with. Unfortunately, we deal it with modern communication. It's selective and fast, unfortunately. Okay? Okay, so this is from today's lecture, and let's in a few minutes speak about the third assignment, because the third assignment is about okay, so
First one is flat and so worst one is selecting fast.
I posted already. Difficult to read, right? You can see it, or difficult to read? Yes, there. Okay, so the third assignment, I give you like almost 2 weeks, right? And you need to read the following papers, right? So as much as you can. The first paper is about to discuss really fading a channel in mobile digital communication. And this paper is published, and it's a magazine paper. Okay, so magazine paper means, I'm not sure if you are familiar with the type of papers, but magazine papers, you mean that less mathematics, right? So there is mathematics there, but like it's very minimal, right? So this, the first paper for this like scientist, he has a book as well, Okay, one of the famous one in this field. So really fading channel and mobile digital communication characterization. And the second paper, similar title but mitigation. Okay, so for this one here, because next lecture, Wednesday, we will be discussing how to mitigate the different types of this fading, because we discussed the type of fading, fast, slow, whatever, right? So next lecture, we will be discussing what is called diversity. Okay, so diversity, one of the techniques that can mitigate or reduce the effect of this fading according to the type of the fading itself. So here, he discussed the fading, and if you open the paper itself, right, so like you go and downloaded it. Okay, so this is the first paper. And if you can see here, this is some kind of similar characterization here. This is a fading channels. This is larger scale, a small scale. In the small scale, we have two types, and we have what I discussed here, but here with more practical overviews. Okay, so you already have the knowledge from the lecture about what is going on here, but you will experience more discussion from practical ways, and you will see some kind of the rules here. Like actually, this is some kind of measurements, and you can see here this is the formula for tau, and this is what I discussed now. Like when I told you the coherence bandwidth is approximately 1 over tau, right? But here is 50, right? According to this reference, okay? According to the behavior of the channel, whatever. Okay, so you don't need actually to include all formulas. It just I need to try to understand what is in practice regarding this fading, because the fading is really important actually to understand if you will continue in this direction. Okay, so I need you to summarize these two papers. The first paper is discussing the fading, right? Large scale, small scale, but with wider perspective regarding to the practical applications. And the second one is the mitigation, how to mitigate this fading. Okay, so he discussed here several types. He repeated some figures again, and if you need actually to copy the figure, it's okay, just write the citation. You don't need actually to reproduce the figure. Okay, so just copy the figure. And again, I need to tell me a story, right? So it's not everything, just like try to understand the main body of the talk here and explain it in your own way. See here the mitigation or compact, fast fading, distortion, and so on, right? So yeah, so there is some ways to, there is what is called a Viterbi equalizer. We'll be speaking about Viterbi equalizer in more details in information theory, right? So like if some of you like taking information theory with me, we'll be discussing in more, here just like general discussion, but I think the last lecture of information theory will be discussing Viterbi equalizer. But anyhow, this is a kind of practical overview. What is fading? How can to compact, or how can you mitigate this fading? Okay, and I expect that this is the two papers, and this is a deadline. Okay, so Wednesday, July 30. Okay, so I think this is the end of the last day of the semester. Okay, so by class time, and you have enough time. Okay, so again, if you miss the deadline or try to work,
last day of the semester is 28. 400 bits, 400 bits.
Yeah, it's changed.
Okay, so submitted by 20. Okay, so anyhow, we will not attend the class here, right? But
There will be class on 30th.
no, it will not be a class, right? But
Only for the assignment.
yes.
So it will be one.
But if you would like to submit by 20th, it's okay, right? You still have 2 more days.
So it will be one column or two columns.
Okay, I will speak about it. Okay, so these 2 papers, you should summarize it and like try like some of you, especially for if you are familiar with this field and if you are working in a research area related to wireless communication, you might know extra equalizers that can mitigate this kind of fading. If you would like to discuss some of them, it's okay, right? So, but it's something like addition. I'm not requiring these from like every student, okay? But anyhow, so what I'm asking you to summarize these 2 papers and try to connect it with what you understood from lecture, because when we speak about the equalizers and diversity, especially diversity coming lecture, you will not, you will hear some different types of diversity that is not or that are not mentioned in the second paper. Okay, so you might include it. Okay, so try to combine between the extra information here in these 2 papers and the extra information from the lecture. Okay, so please provide summary of the 2 papers by using your own words. Okay, which ChatGPT. Okay, so I have AI detector. Using your own words, 10 pages max. Okay, and I would like actually to use 2 columns, but if you have, if you can use one single column, it's up to you. But again, you might suffer from like 10 pages only, might like very lack of space because you might use some figures from the 2 papers. But again, I need a complete idea. So if you can discuss this complete idea in single column, it's okay. If you cannot, you can use double column, okay? So it depends on your creativity, and some people can express and hit the target in a few words, some needs more words, right? So you have a flexibility of maximum 10 pages. You can use 5, you can, but again, if I see that you're missing, not missing equations, I'm missing ideas, big ideas, right? So for example, you discussed a slow fading, but you didn't discuss, for example, the mitigation method for it, right? So you missed ideas. But for, let's say, for mitigating a slow fading, for example, you have 5 equalizers. You discuss 2 or 3, it's okay. Okay, so at least you cover the whole points to understand the topic. You don't need actually to explain everything. So that's why you have a wide range, 10 pages max, single column or double column according to your preference.
So should we provide the summary like topic by topic as given in the review?
As a story, right? So you have abstract, because both of these topics, even if you open the second paper, you will find it repeated the introduction as well. See here? This is the characterization. Look at here, this figure, and also this figure as well. Right, so if you open the second paper, he repeated also the introduction, because actually both introductions almost the same. I'm speaking about the fading, right? And I have section to define what is fading, another section to define how can you mitigate this fading. So it's one paper, the summary is one paper, one story, right? You know what I mean?
So our topics or the headlines of subtopics should be like introduction, methodology.
Yes, similar to any paper, right? So you have exactly like abstract, but the abstract now, you will discuss in the abstract that you are trying to take a deeper look about fading and how to mitigate, how to define, right? So, and like introduction, you use your own introduction. But again, these two papers is pretty close to each other. One tackling the issue, or one is discussing the issue, and another one tackling the same issue, right? So you can form one story, one paper, right? Don't say paper one, paper two, no, one story, right? Is it clear? Yeah. Any more questions? And like, if you try to open these papers and like make some kind of a general vision how to address this assignment, and come to me, and if you have more questions about it, next lecture you can ask, right? But again, don't wait until last minute, okay? Because yeah, I will not accept, right? So you have 2 weeks. Okay guys, so that's it from today's lecture, and